please join me in welcoming to the Distinctive Voices podium, Dr. Alissa Crans.
Great, thank you so much. Thank you so much. It's really a pleasure to be here because my mother worked for Beckman her entire career. So it's really, really quite an honor to be here. That was a lovely introduction, all of which is true, none of which we're going to talk about today. So I want to give you a heads up that nothing that we're going to do today is my original work. What I wanted to do was share with you some mathematics that I think is beautiful and fun and creative, and hopefully dispel the myth that math is those horrible formulas that we memorize in high school. But first, I want to share a little bit about myself. So I play the clarinet. I have for a very, very long time. I enjoy doing things outside, so I like running and competing in triathlons. I also really enjoy baking cake. I also really enjoy eating the cake, but baking and decorating is one of my true loves. And I've always wanted to be a teacher. This is me in the 4th grade, dressed up for career day as what I thought a teacher looked like. One of the things that I've recently spent a lot of time doing is raising a guide dog. So this is Hobie. We had her from 8 weeks and trained her for about 15 months or so. We turned her in to be trained by people who know what they're doing with dogs for people who need them. And we got a call saying she was chosen to be a breeder for the program. Would we host her again? So spent lots of time with this little one. As was mentioned, as Jennifer mentioned, I went to grad school at UCR. And I've spent some time at a bunch of different institutions. So I've been at Loyola Marymount since I finished my degree, but I've spent some time teaching at Ohio State, the University of Chicago, and most recently at Carnegie Mellon. The professional activity that I am most proud of is this conference. This was an undergraduate conference for math majors. We ran this for 10 years, and we had, in the very first year, 48 people attend. In our final year, over 700. So this was, like I said, the professional activity that I was involved in that I am most proud of and that I had the most fun doing. These are a bunch of student groups that had attended our conference. And finally, if you are interested in other mathematical opportunities for yourself, your children, your grandchildren, please come see me. These are a bunch of activities and places that I've been involved with, and be happy to share more about them or how you could get involved both in person and virtually in other mathematical activities in the Southern California area, but also nationally. All right, so you might have been warned that there's going to be some audience participation today. Okay, so that's why we're in this room and we're not in the lecture hall. So the first thing I want us to do is a warm-up activity. You're going to respond on your phones. Don't talk to the person next to you. I want you to answer this for yourself. Which one of these does not belong? And you can go to this website and choose which one, and then we'll talk about it together. Yes, yes, so yes. Please, yes, turn your phones back on first. All right, I'm seeing all of your answers pop up here. Let's take maybe another 15 seconds or so to respond. All right, what if I told you? You're all right. Talk to the people at your table. Which one did you choose and why? All right, anyone who voted for 1, are you willing to share why you voted for 1? Yeah, how about in the back? Go ahead. Why did you vote for 1? Okay, yeah. So why did you like it? Why do you think it didn't belong? Okay. Yeah, so I heard someone give a reason. Yeah, go ahead. It's the only red one. Okay, so that doesn't belong because it's the only red one. Perfect. Who voted for 2? Great, yeah, do you want to share why? Yes, it's the biggest one, so it doesn't belong because it's the biggest one. What about 3? Did anyone vote for 3? Yeah, go ahead. Yeah, good. Yeah, so this one is rotated from the others. And then 4, anyone vote for 4? Yeah, go ahead. Yeah, good, good. This is the only rectangle. Great, okay? What I love about this activity is it shows that in math, there doesn't have to just be one right answer. Right? So let's do one more. Now it's a bit more interesting. So go ahead and cast your vote for this one. The one with the fewest number of votes right now is D. So what I want you to do at your tables is talk to each other, come up with a reason why D doesn't belong. Oh, I'm sorry, 4. 4. Thank you, 4. Yeah, why does 4 not belong? Chat with each other. This is the one that has the fewest votes. Why is 4 the one that doesn't belong? Convince each other. Go ahead. Did any of your tables come up with a reason for why 4 doesn't belong? What makes 4 unique amongst all of these? Yeah, go ahead. Yeah, no.
Oh, thank you, Jennifer. So I was thinking that if you divided it into triangles, they wouldn't be the same size. And the other ones, I think you could get them divided into triangles that were.
And that'll work? Yeah. Yeah, good. Did other tables come up with yeah, go ahead.
The flat top, the other ones are all having an angle.
Good, does everyone see that? Yeah. Other reasons for why 4, yeah, go ahead. With an obtuse angle? So that's an angle that's bigger than 90 degrees? Yeah, go ahead. Oh, so can you bring the mic back up here? Will you share again?
Number 4 has a flat top, whereas all the other ones are pointing inwards with a pointed angle. Yeah.
Great. And then do we hear the only one with the obtuse angle? Is it 3 also does? Okay. Okay. So yeah, go ahead in the back.
So 4 is the only one that has the number of sides.
That has the number of sides. Oh, as the label. Is that true? Wonderful. Great. Great. Any other reasons? Yeah, go ahead. Good. Yeah, this one has no symmetry. We can't like flip it over any axis and get it back. Now, it's also the only one with 2 right angles. Right? So we could come up with arguments for any of these 4 for why they don't belong. Right? So again, if you like these sort of activities, there's an entire book consisting of every single page. It has numbers, it has shapes, it has symbols. Okay, so great, great book, especially for young children who, are learning what math is and think that math is about numbers. I hate to tell you, math is a little bit about numbers, but mostly it's not. All right. Again, I've got some math I want to share with you, and I'm really excited to get to share it with you. But before we do that, I wanted us to have a little discussion about what does it mean to study mathematics or do research in mathematics, right? We might have an idea of what biologists do. Maybe they work with animals, or chemists, they're in a lab, or physicists, or maybe you even know what historians do or archaeologists. But what does a mathematician do, right? What pops in your head is like, what do I do when I'm doing mathematics? And so what does it mean to discover or create new mathematics? So this is something that my students struggle with. They think all math is known. It's in every textbook that exists. And that couldn't be farther from the truth. And what do we do all day? Okay. So again, we sort of know what chemists and biologists do and some physics folks, but what do we mathematicians do? One of the things we do is we identify patterns. Now, not just patterns amongst numbers, although that's what this example is going to show us. So what I'd like you to do is, with folks at your table, fill in the right column. What are these sums? And what pattern are you noticing? So go ahead, take a couple of minutes, talk to folks at your table. What are we noticing? What's the pattern that's going on here? All right, so let's look and see what we're noticing here. What's true about these numbers that I'm filling in here? So if I add up, so what am I adding on the left and what am I getting over on the right? So again, go ahead and chat with each other. I heard a bunch of people say it. We're getting perfect squares over here. Now here's the thing. We only did a few examples, 5 examples, right? And we guessed that this is the pattern that we're seeing. Now, just looking at 5 examples, that's not enough for a mathematician to be convinced that that's what the pattern is. Looking at 100 examples, that's not enough. Looking at 1,000,000 examples, that's not enough. What separates mathematics from the other scientific disciplines is the notion of mathematical proof. The science disciplines have the theory of evolution or the theory of relativity, but they can't prove that these are true. I can prove to you that the sum of 2 even numbers is even. I can also prove to you that this statement here is true, always, no matter what n is. Now, you might feel that that wouldn't be any fun, and we're here to have some fun, right? We're not here to do school math. So what I'd like to do is I'd like to give you a picture proof of this fact. So I'm going to start with 1. I'm now going to add 3 to it. Now we'll add 5. And so on. So we see the perfect squares staring us in the face. Okay, so this is where this result comes from. I want you to stare at this table, talk to people at your table. Do you notice a pattern here? What do you think is going on? What are we noticing is true here? So go ahead, chat with each other. What do you see here? Oh, we have a guest from the middle of the room. Do you want to say that louder?
It looks like all even numbers can be sum of 2 primes.
Do we see that? That's what it looks like. Yeah, that's what it looks like. This is called Goldbach's conjecture. The statement that was just made was a statement that was made hundreds of years ago. We do not have a proof of this statement. Okay? I love this because it's so simple to state and seems tantalizingly easy to show. But it's not. So we have verified this statement for millions and millions and millions of numbers, okay, using a computer. But that's not a proof. Okay? So if you want to prove this, you will be famous beyond your wildest dreams. People have been looking for a proof of this for a very long time. So we don't have a proof that it's true. We also don't have a proof that it's not true. Okay, so this is an outstanding problem in mathematics, one of my favorites to talk about. What else do mathematicians do? We ask questions. We're very curious. So hopefully from high school you remember the Pythagorean theorem, and hopefully your teacher did their job and showed you what this means, what a squared is, what b squared is, and what c squared is. A squared is the area of the square that I can draw whose side length is the length of A, that side of the triangle. Same with b squared and c squared. So what this result is actually saying is that the area of the yellow square is the same as the area of the blue square plus the area of the green square. All right, so this is true. We've known this for a very long time. What do I mean when I say mathematicians ask questions? Well, what if instead of drawing squares on all sides of the triangle, I drew circles whose diameter is the sides of the triangle? Is this still true? Is the area of the yellow circle equal to the area of the blue circle plus the area of the green circle? What if I draw equilateral triangles? Is that still the same? Is the area of the yellow equal to the area of the blue plus the area of the green? So a common thing that mathematicians do is start with a result that we know is true, have known is true for a very long time, and we change the question just ever so slightly, right? We change from squares to these other shapes that we know. Okay. This leads to lots and lots of generalizations of facts that are hundreds of years old. All right, now let's do some new-ish mathematics. right? Geometry is many, 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 many years old. Let's talk about something that's more recent. So those of you who have your phones and can go to this site, you are going to see a menu on your left that looks like this. So I want you to click on the geometry. And you're going to notice that you have all of these shapes. And you're able to like click on one and drag it into the blank space if you want to play with it. And I want us to focus on just those top 6 ones. Okay, so just these ones. So again, this is under the geometry heading on the left. And I want us to just play with these ones here. Okay, so here's my question. Suppose you're going to remodel your bathroom. And you want to get some new tile for your bathroom. You're only allowed to choose one of these. Which ones, or one, of these 6 shapes could you use to tile your bathroom so that there's no gaps in between them when you put them on the ground? Okay, so you can talk to people at your table, you can work together. I want to know which of these 6 shapes would allow us to tile our bathroom floor without leaving any space in between them. Oh, really? It's asking you to sign in, everyone? Yeah, the question is you're allowed to use exactly one of these to tile your bathroom floor so that they all fit together nicely and there's no gaps in between them. All right, so let's check in together. So can I have someone give me one of them? Either you can say the name of the shape if you remember it, or you can tell me the color of this shape. So anyone willing to give me one of these that will work?
The square.
The square. All right, yes, the square will work to tile our floors. Wonderful. Someone else? Can you? Yeah, Declan. The triangle. Yeah, the triangle also works to tile the floor. I should say the reason why I know this person's name is he's my nephew. All right, final. Yeah, go ahead. The hexagon. Yeah, so we could have a hexagonal floor. Super. So I only did a few of those, but right, if we tile the floor with squares, they'll look like this. Triangles and hexagons. Now, those of you who are playing with the app might have noticed that the 5-sided figure, the pentagon, that's not going to work. Okay? And maybe you say, oh, well, Alyssa, move the blue one over. Maybe it'll fit better, and we won't have that gap problem. But I assure you, we will always have the gap problem. Okay, so these shapes are called regular because they have the same, their sides all have the same length, and their angles are all the same. So we could never, never have a contractor come and tile our floor with these pentagons. So, about 100 years ago, mathematicians asked the question, these pentagons don't work, the regular ones don't. can we change the question ever so slightly? Are there other 5-sided shapes that will tile the floor? Okay, what is this special word, convex? That just means that none of my sides are allowed to dip inward into the figure. Okay? I love this story. I'm so excited to get to share this with you. So, in 1918, Karl Reinhardt discovered 5 different pentagons, 5-sided shapes, that were able to tile the floor. So here are 2 of them, and here's the other 3. 5 decades later, someone discovered 3 more of these pentagons. So Kirchner discovered these 3 patterns. And now Kirchner claimed that was it. There were only the 5 that we had 50 years ago, and then the 3 that he discovered. This came to the attention of someone named Martin Gardner. Some of you may be familiar with some of his columns. He is hands down the undisputed master of popularizing mathematics in this country. He had a column for a long, long time in Scientific American called Mathematical Games. And so this story came across his plate, and he decided to share it with his readers. Now, this column, in which he said, they've all been found, well, those of you who are familiar with this column, or maybe his readers, might know that his readers don't take everything at face value. So it inspired readers to look for other shapes that also satisfied this, and sure enough, another one was found. So Kirchner was not correct that he had found the final 3. It turns out that the floor in the mathematics department of Ohio State University uses this tiling pattern outside of their lobby of their elevators. Okay, it looks like that. Two years later, this brings us to sort of the hero of the story, Marjorie Rice. Marjorie was not a professional mathematician. She only had a high school education. She just loved mathematics. She read the column in Gardner's article, and she was inspired to just try, looking for ones at home by herself. She found 4 unknown pentagons. Here they are. Because she was not a mathematician, because Martin Gardner was also not a professional mathematician, he shared Marjorie's findings with a professional mathematician, Doris, who took it and shared it with the mathematical community at large. Okay, so Doris was able to publish Marjorie's work, showing that she had come up with these 4 new shapes. So this is what the tiling looks like for one of Marjorie's pentagons. And here's what it looks like on the floor. The story went cold for about 30 years. Oh, hold on. Until there was a 14th one that was discovered in 1985. And then, fairly recently for mathematics, right, 2015, the 15th version was found, and this was a research project with undergraduates at the University of Washington. So it was a group of undergrads together with their faculty mentor who found a 15th type. 2 years later, oh, well, let me share. Like, this was a big deal at the time. Okay, so we had big announcements in the mathematical community. And this is a building in Europe that used the 15th family to decorate its outside. 2 years later, Michael Rao proved we're done. So I know I told you earlier in this story that someone claimed that we were done, but Ralph proved that we were done. Okay? So there are only 15 of these, and we've discovered all of them. What I would like to give you some time to do is I have all the 15. I want to see if you can put together the tilings at your tables. Now, I'm going to warn you, this is not easy. All right, so what I'll do is I'll pass them out. Feel free at your tables to work on a few of them. And I'll come around and give hints once you get too frustrated. Here's a couple for your table. Oops, oh, I'm sorry. Oops, pardon me, I'm sorry. Those of you who are more inclined to use your phone, these are on that Polypad website. They are located underneath the shapes that we started with. So if you would rather try these on your phone, you can do so. I'll give you guys a purple one and a white one. Do you guys want a different one as well? Or are you, so if you would like to play with another family. I think that be careful, the different color, so the blue ones go with the blue, the yellows go with the yellow. So yeah, you should only be using a single color and not mixing and matching them, otherwise it will not work out. I don't know if you guys want another, oh, you've got 3. Do you guys want another color to work with? Okay, so again, they are available on the website. They're listed as the pentagon tilings, and I've labeled the 4 that Marjorie Rice came up with, and then the 15th one, the final one that was discovered in 2015. So let me give you some time to try these, and then I'll come around and offer some hints. You guys type 3. So if you want to see how they fit together, yeah. So what I'm going to be passing out now is sort of a hint for how yours fit together. So when I come by, if you can tell me which type you have on your bag, I can give you the 5. Great, so this is the basic pattern for how those go together. And then the yellow is at 14? 7, okay. Yeah, sure, go ahead, take them out. The yellow ones go with the yellow, and then the blue ones, so that shows you, well, so this is the basic pattern, and so you'll want to fit those together. So if you see that shape in what you put together, that tells you how to fit them together, yeah. You guys have 11. Okay, so here is the sort of basic building block for 11. And here's, oh, I'm sorry, I gave you both orange. That, yeah, must be confusing. You guys have 10. Okay, so, yeah, so here is this is the sort of secret decoder ring of how these ones fit together, so you guys can check that one out. You guys have type 6. All right, so this is the pattern that will fit together to show. Yeah, so this is the, let's see, so 14 will go together like this. You should feel free to take them out and put these together. Type 1 goes together a bunch like this. Ah, so you guys have the most recent one. Yeah, that one is really intricate. Let's see, so 12 and 9. Yeah, so 9, if you want to take these apart and fit those together to see how they go, that shows you the tiling. All right, type 8 will fit together like this, and type 2, you'll get a bunch of patterns that look like this. And feel free to take them out and put them together and see how those fit together. All right, I'll give you some more time to play with these in a little bit. I want to tell you a quick related story that's even more recent than the end of the Pentagon story. So all of these patterns that we talked about at the beginning, so the tilings that we came up with at the beginning, these are all examples of what is called periodic tilings. What that means is that I could pick this up and move it to another section of your floor, and it would lie on top of it exactly. It would match up exactly. So those of you like me who remember overhead transparencies, if you imagine that I drew an overhead transparency of this, picked up the overhead, and put it down somewhere else, it would exactly match up. Okay, so these are called periodic tilings. Mathematicians have known about periodic tilings for hundreds and hundreds of years. In the 1960s, people were interested in the question, can we come up with some number of set of shapes where when we tile the floor, it's not periodic? Meaning if I picked it up and slid it over and put it down, it would not match up. Okay, so is there a collection of shapes for which we can do that? So the person that posed the question, he thought that this was impossible. But his PhD student was able to produce an answer to this. Unfortunately, he used, about 10,000 tiles. Okay. People didn't want to have to deal with that many tiles, but fortunately, he brought the number down to about 100. Okay. So the quest began for how few tiles can we use to come up with this sort of tiling pattern. And Roger Penrose brought the number all the way down to 6 in the 1970s. So this is an example of a non-periodic tiling, meaning if I picked that up and slid it over elsewhere in the room and put it down, it would not match up. He came up with another one that only involved 2 tiles. Okay. So what's the question that mathematicians were dying to know, obviously? Is there one? Can we do it with just one? This is called an aperiodic, meaning not periodic, monotile, a single tile. So this is like hot off the presses in terms of a mathematical timeline. This is brand new mathematics that was just discovered. Some of you might have remembered reading about this. It was big news, okay, when it came out. So a couple of years ago, David Smith, an amateur mathematician, discovered a shape that he believed satisfied this property. A single shape that he could tile the whole plane and not be able to pick it up and slide it down. He had been interested in the problem for about 5 years and working on it. He sent his information to a computer science professor in Canada. They brought in 2 other experts in this area, and in November of 2022, they announced that they had found the hat tile. Okay. I like to think of it as the t-shirt tile myself, but they refer to this as the hat. Okay. These are the other 3 that were brought in to verify that the shape did what they wanted it to do. And this was big, big news. Okay? Those of us who study mathematics loved the press that we got for the discovery of some new mathematics. You quickly could buy anything you wanted on Etsy in the shape of this new tile. Okay? Notice there are some cookie cutters even. Now, yes, I think these are ravioli. It's called an Einstein. That in German means one tile or one shape. Okay. There was a tiny, 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 teeny, tiny issue with this. You couldn't just take the t-shirt and lie it on the ground over and over. At some point, you had to flip it over. Okay, so the starred shape are the ones that use that version of the t-shirt. The yellow stars, you had to flip it over. So this was not 100% satisfactory, as you might imagine. So we kept looking. As they continued the quest to try and narrow it down to one that you didn't have to flip, they discovered the turtle. Okay. It turned out that you could start with the hat and continuously morph this shape into the turtle shape. So not only was there the hat and the turtle, there were infinitely many shapes in between that satisfied this property. So like not only did they discover one, they discovered an infinite family of shapes that did the job. Okay? Again, I can't emphasize enough what a big deal this was. And moreover, if you look here, what we're getting right here is a hexagon. We have the missing pieces down here. But so people were like, oh, how could we have missed this for hundreds of years? We've known about the hexagonal tiling forever. How did we not discover this? Okay, this was, I really can't emphasize enough how exciting this was. Okay? But again, this led to the question, can we get it down to a single tile that we don't have to do the flip? And some of you know the punchline. Yes. A few months later, the Spectre tile. Okay. And it was named because, I guess, something related to vampires. They can't like flip in the mirror or something and see themselves. I don't really know exactly what that was about, but so now we've done it. Okay, we've answered the question. We have a single tile. This will cover the floor, no gaps in between. And I can't pick up a section of the floor, move it over, lay it down, and have it match up. I have for you hat and Spectre tiles to play with. Okay, so if you would like to play with the pentagon some more, you are welcome to. I will also give you some of each of the hat and the Spectre tiles, should you wish to play with those instead. Okay, so I can walk around. Oops, I'm very sorry. These are the hats. I can walk around and offer some suggestions or guidance. These are the Spectres. let's see, I can give a couple of each. Yeah. Remember, for the hats, you need to flip one every so often to get them to work. That one is the specter. That's the one that you don't need to flip. So for that version, those are indeed curved. For the one that is 3D printed for you, they are straight. Yes. Ooh, that looks great. Does it match up with? So this is the basic building block for the two. So if you see that shape in here, so you have these and you have these. Yeah, so what that means apparently is that that will not be able to infinitely. So what you've done will not be able to infinitely. So it works for this little patch that you've done, but yeah, but it won't be able to do it on and on forever. Yeah. Let's see. Yeah, so those are some hats. These are the specters. Yeah. And when you're ready for it, if you want to peek at the back of the book, I'll put on your table. This is the hat tiling. So if you would like, you can flip it over and check your hat tiling to see whether or not what you've done agrees. So on the screen now is the version of the specter that you all have. The one on the left with the straight sides. The curly one, it was too hard to 3D print. So that's why you guys don't have that one. So remember, when you're doing the hat, every so often you'll need to flip one of them. And for those of you who are doing this on your phones, these also appear on the same website. They're the monotile, and they have both the hat tile and the specter tile. So those are the two stories that I wanted to share with you today. I want to thank you very, very much for coming out. You are welcome to play with these as long as you'd like. I'm also happy to answer questions either about this. So remember, this is not mathematics that I am responsible for. I'm happy to try and answer questions about these, but I'm also happy to answer other questions in general. But thank you so much for your time.